Hey there. So I've been doing Go for a little while, and while I love the language, its simplicity, it's great. I love the language, but my favorite feature is the toolchain. The Go toolchain, just that Go command. It's great. We can do all kinds of things. So we can build, we can test, we can format our source code, we can get dependencies, we can do code coverage, we can do performance profiling, we can do race detection, like all those things. It's crazy. But as we start to get into it, we spend 99% of our time inside that tool, but there's that 1%, what's that next step? So as developers, we want to kind of build our own tools. So we start to do that, and we start simple. Maybe we start with code generation. So we have simple print statements, put out some code, and we, generate some boilerplate, which is only so useful. Next, we might go to, the Go sub packages. So we have Go AST, we can parse, we can scan, tokenize, we can get this abstract syntax tree. We can do a lot of stuff with that. So I wrote a tool called MegaJSON a while back, and it's great. We can parse out a Go program, get the structs for it, generate JSON decoders, encoders, and it's a great use case for that kind of thing. So this is it's a popular approach. If you go on godoc.org, you can see that over 1,000 packages import Go AST. But the AST is limiting, so it only shows the structure of your code, kind of the layout of it, but not how your data flows through. So we want to move on to something bigger and more advanced. So we can use static single assignment intermediate representation, which is quite a mouthful, and there's a much simpler way to say it, SSA IR. That's what we're going to talk about today. And why does it matter, and why is it useful? So SSA IR, it shows how your code flows and how your data flows from different variables to different functions, different blocks and sections of your code, and how those values flow through. And the best part about SSA is there's a package for it, written by Alan Dalnovan, who's here. I actually met him the first time at the kickoff party. And if you're around, raise your hand. Yeah, right there. He'll answer all your questions later. He's also very well dressed. He always dresses up nice. Best dressed person in the Go community. So yeah, he's the primary author. Really smart guy. I've read through his code, and used this a bunch. It's a great package. He's also written this book here coming out, and I gave him a hard time for this, but he wrote it with Brian Kernighan and somehow got his name first. I don't know how that works out. It turns out they did it alphabetically. While Go AST is really popular, you go on godoc.org, and only 5 projects import this package. It's very powerful, but I feel like it's the most underappreciated package in the Go community. And how few is 5 packages or projects? You can fit them all on one slide, and this is everyone out there that actually imports it. So let's break down SSA IR. So intermediate representation, let's start with the IR part. So all that means is that we have a layer in our code, our representation, that sits in between our Go code and our machine code. So our Go code is where the AST lives. It's kind of the structure of our code. And it shows the layout, but it doesn't show kind of that flow of data. Whereas the machine code, it'll actually kind of show the flow between jumps and registers, but it's all machine specific. So we need something right in between. And IR is high level, so you still have these Go concepts like Go routines, and you have functions and types, but it's also, it's portable. So we can actually run it on AMD 64, we can run it on an ARM processor. It's all the same code that we analyze. Okay, so that's the IR part. Let's talk about SSA. It stands for static single assignment. I actually spent time practicing saying static single assignment intermediate representation because it's that hard. So this is normal Go code that you normally see. You set x to 1, y to 2, and now we set x to x plus y. But this isn't allowed in SSA. So the problem is that we can't override our variables. We can only set them once. That's the single assignment part of it. So what we do is we version the variables. So we have an x1 now, that's 1. We have a y1, that's 2. And then now we can see x2 comes from these 2 other variables, these versions of the variable. Now you see this a lot in in functional languages. But when you take your Go code, you can bring it down to this SSA form. You get a lot of that benefit of single assignment. So having these versions and being able to track where your values come from and following that flow makes the analysis easier when you're trying to analyze your code. Okay, let's talk about a couple terms inside of SSA. A lot of people find it daunting, but there's a lot of overlap between Go and SSA. So first, at a high level, you have a program. So that's basically, it's a collection of all your packages in your program. And since Go, it's statically compiled, so you have all of your packages at one time, at compile time. It's kind of your whole view of your whole world. And this includes all your dependencies as well. And then inside of there, you have your packages. So you have types, you have functions, all those top-level constructs. Now we drop down into functions, and this is where it gets a little more interesting, a little different. So we have a function, and your function signature is the same, but inside your function, you start to get what are called basic blocks. So a basic block is simply a contiguous set of instructions that are executed that can't jump anywhere else. So for example, this print right here, you'll always execute that, and then you'll execute the read string right after that. You can't ever jump somewhere else in your code. And these basic blocks get linked together through jumps and conditions and whatnot. Now, the way that we had it right here is how you actually code it up. But in my head, I think of it as a control flow graph. So we have our if statement, and if it's true, it goes over to this block. If it's false, it comes down to this other block. And once the true block is true, then it goes down to that final block. We can look back, and that's kind of how it flows in our head. OK, so once we drop down from inside our basic block, we have instructions. An instruction is simply something that operates on values. So we can have like a binary operation, like our equality operator. We can have a function call. We can have an assignment. There's a lot of different instructions, but they all operate on values. And we also have values. So value is something that simply has a value. It's pretty straightforward. And there's a lot of overlap between instructions and values. So you can say that the function call, it'll take values into it, but it can also return a value to you. So this is a small language that we can construct with these SSA IR primitives. And this can describe every Go program that's out there. And a lot of these look familiar. You might see like the Go for Go routine, or you might see like an if statement. Those are all kind of similar things. But like an alloc, you might not be used to, or like a phi node. These are some more specific lower level SSA constructs. OK, so that's a lot of the terminology and a lot of how the stuff works kind of in a theoretical piece. But what does it actually look like? So if we have this program here, it's kind of our hello world program. It's a CLI application. We pass in a name, and then it says hello back to us. So here we'll parse the flags. Then we'll check to see if the number of arguments is 0. If it is, we'll print out and say that, this is the actual usage, and then exit. If it's false, we'll jump down to the bottom and grab the argument, say hello, and then we say hello. Pretty simple. No questions? OK. So if we actually take that program and throw it through SSA dump, which will actually parse our Go program and then create the SSA for it, and then dump out a text representation of our SSA, we get this thing, which it looks kind of weird. It's like Go meets assembly. And you look at this, and if you squint real carefully, you can kind of see how our old program is in there. You see some calls to different functions. But you see a bunch of weird stuff in there, too. So let's step through this. So first, we start off when we have our func main. And this is the same as we had in our Go program. It's a function signature. And then inside of here, we have our basic blocks. So these are sets of instructions that each one will run one after another until it gets to the end, and then it will jump somewhere or return back somewhere. And then each one of those are numbered in increasing order. So we have 0 block, 1 block, 2 block. OK, let's start with the first one. So the 0 block is the one you always start with in a function. And there's a name over here on the right. It's called entry. The P over there stands for predecessors. That's how many blocks come into this block. And the S is successors. That's how many blocks it flows out to. So as we walk down this, we can see a lot of that, the stuff from our Go program. So here we're going to parse, and it returns an error, which we actually don't use, but it's still shown in our SSA. And we grab the number of arguments. And this is our if block right here, our if line. So that if was one line before, but when you actually get in there, there's 3 different instructions that are going on. So first we do the function call and get the number of arguments back. And that goes into T1. That's a variable. And then next it goes down, and we're trying to compare T1 to 0. And that goes on another variable. That's T2. And then we jump down, we have an if instruction. And if T2 is true, we're going to go to the 1 block. If it's false, we're going to go to the 2 block. So we walk down that. And then if it's true, we're going to hop right here. False goes down there. So inside of our true block, this is where we want to print out our usage. Now our usage print was 2 lines before, and now it's like 8. So it's a big jump. But there's a lot of things going on underneath that we just don't know about typically that Go handles for us. There's all kinds of things like when you try to call a function on a non-pointer, but it has a pointer function. There's all that kind of things that Go helps you out with that you never see. But in SSA form, it shows you every little thing it does. So with our print, print line, it actually takes a variadic set of arguments of interfaces. So we passed in 1 argument, but we need to construct that array that slice and then pass those arguments in. So here we're constructing a size 1 array of interfaces. And we're going to grab a reference to that first variable in there. And notice how we're constantly creating variables in here. So we can start to move through this flow of where these values are going to. And then we're going to actually convert our string into an interface. And then take that new value and put it into the address that points to T4, which is our first position. And then we're going to create a slice from that array. And finally, we actually call println with that new array. So all those steps in there are actually what's going on underneath. And then finally, we call out to OS exit. We get an error back, which we, again, don't use, but it's still shown in our SSA. And then we get this jump down here at the end. We would think that the OS exit would just exit our program, but the SSA form doesn't understand that OS exit is a syscall and goes out and kills your program. So it assumes it's just a regular function. Now, in the false case where we actually do have an argument, we're going to grab that argument and put it into T9 and pass T9 to our function, say hello. And that's the whole program. And we're going to return out. Now, we have this kind of assembly sort of looking thing. If we actually look at the variables in there, we can kind of see how they start to flow and how certain variables turn into other variables and compose into other pieces, and which versions of which variables are used where. So you can see like T3 gets used in 2 different places, when we grab the first index and then when we reslice it. So we can start to flow through this graph of where our data is going. We can also start to draw lines between blocks and see how one relates to another and where they flow. So our entry block, it goes into other blocks. And a lot of these examples are fairly simple because they fit on the slide, but obviously a lot of functions out there have many blocks and if statements and selects and for loops and all kinds of branching. That's going to make kind of more of a tangled web that it helps to visualize in this way. OK, so that's a lot of theory that we're talking about so far, and we want to talk about practical applications. And if we want to talk about theory all day, we'd be at a Haskell conference, but we're at a Go conference. Got a jab at Haskell. Sorry, guys. So tools built on Go SSA. There's a lot of stuff that's being put out there. I mean, there's a few packages in the community. I really hope to see more. There's some cool stuff you can do with it. It's really powerful. Let's see what people are doing, though. So there's a tool called SafeSQL, which is really interesting. It comes out of Stripe from a guy named Carl Jackson. And it actually goes through and finds calls to your database SQL calls and checks to see that the query string that you're passing in is a compile time constant. And this helps to prevent SQL injection, because you don't want to get random input. So our SafeSQL, this is an example program we have. where we're going to open the database, and we're going to grab a favorite color off the command line, and then just throw it into our SQL. This is a bad idea, because if your favorite color happens to be drop table, then you have some problems. So we're going to get our color right here, and there's our SQL injection. It's a potential issue. And if we run safe SQL, we'll actually get an error where it'll say, this is the line where we have potentially unsafe SQL. You should do something about that. And kudos to him, definitely for Carl, because he actually gives a real message about why you want to do this. And whenever you're building static analysis tools, so many are so obtuse, you don't really know what the error message is or why you care. But he explains it really well. So you always want to use parameterized queries and make sure you only use compile time constants. Here's another example where we have a favorite color, but it's hard-coded, and it's a constant in there. So we're still doing that concatenation, but we can figure out through these SSA packages and other tools inside the xtools library that this is actually a compile time constant. When we run this, we actually say, let's say from SQL injection, and we get ASCII art, which is even better. There's another tool called Oracle, which again, Alan Donovan is the main author of that one. You can do some really cool things around finding, given a variable in a specific location in your code, what kind of values got to that, where it's being used. You can get, you can get all kinds of insights about your code. And the more important thing is this will actually work with interfaces too. So even if the simple cases where you have a struct, and you know that's always going to call this function, but if you have an interface with a lot of things that could implement it, you want to know exactly which implementers of that interface could be called in a specific location. And this actually uses the pointer analysis subpackage, which is it's a great package. It actually analyzes your whole program to figure out all the different possibilities for where code can flow and values can flow. And here's a list of some of the things that Oracle could do. So you can find what code calls a function, what code is called by a function. You can trace possible paths to code. You can figure out what implements an interface, even within your whole Go path. You can say what implements reader. You can find who sends to and receives from a given channel, given that value and where it gets passed to. You can figure out different possible values that could be in a pointer, even if it's an interface. You can also find other identifiers that have the same value, so it's been passed around. So there's a couple different options we can put on there. We'll try a couple here. So we have callees. So callees will let us see for a specific location in our code what things could possibly, what types could be called. So here we have an interface I with implementations of T and V. And on here we have our X, which is going to be of type I. And initially we set it to a pointer of T. And if we try to check the callees right here at this first instance of x.foo, we'll get a list saying this is a dynamic method call because it's an interface, and that it could only be T at this point. So if we look again, we can see, obviously it couldn't be V because V hasn't been set to that variable yet. Although if we come down to the bottom and we check this x.foo, we can see that given the value of condition that gets passed in, it could be either a pointer to T or a pointer to V. And when we actually check that, we can see that it could be T or V on here. So this actually follows the path of where the values are being passed and deduces what the possibilities or what possible types could be in there. And this obviously gets much more interesting once you have a whole program and not a single main function, but you get the idea of how you can give it a piece of code, a specific place in your code, and figure this stuff out. There's also Oracle.callers, where we can take a function, say T right here. So our T, we're setting it to I, or setting it to X down at the bottom, but then we're immediately overriding that with V. So the naive implementation of trying to figure out if T is called would simply be that we see it gets instantiated and later called, so it's probably called in our program. But if we use Oracle, it'll actually trace and figure out that value at that point in time at the bottom with x.foo, it could never be T because it gets overwritten. So we call callers on that, and it says that t.foo is not reachable. This is good for figuring out some dead code in your system, or to figure out just where a function could actually be called in your system. Now, if we do the same thing with the v.foo, and down here, because we overwrote x with v, it'll actually tell us that it gets called in that location at the bottom. Another cool one in a similar vein is points to. So with this one, we can actually see at a given location in our code, what are the possible values of this thing that this variable could point to, even if it's an interface. So here we have x with type I, and if we check what could be in x at this location, it has to be t, and we call that and we call points to. It'll actually say this may point to pointer of t. Now, if we do the same thing and call it down here where it gets overwritten, it can only be v, and again, points to tells us that. But now at the bottom, if we try to figure out what's in x, and we call it at this location, depending on the value of our condition, it could be either pointer to t or pointer to v. And we call that, it tells us it could be either one. And again, these are the simple cases to help understand it, but once you start getting branches and loops, this gets much more complicated to figure out. And having these helpful tools helps us analyze and understand our program. So the last tool I wanted to talk about was one called GoRename. If you haven't heard of this or used it, I know a lot of people have. It's a really useful tool. It's like search and replace, but you don't get all the errors that you do from actually just using sed or grep. So it safely renames your identifiers. So given an identifier in your code, you can actually rename it in all instances, not just in your program, but it could be across your whole Go path. If you have a library, for example, or it's a dependency of something else, you can actually go through and rename all the instances of it in a safe way and give you errors if it has issues with this. And this actually uses the Go types package, which kudos to Robert Grissomer, who just spoke. He was the main author of that. It doesn't use SSAs, but it is a really cool package, so I wanted to mention it here because it is static analysis, and we have such a dearth of tools out there for static analysis. So what it does is it prevents ambiguity and shadowing conflicts. And if you don't know what that is, you're much like me, I don't know, a few months ago, and I had no idea, so I had to look it up. And a shadowing conflict is where you have a variable like x right here. If I wanted to rename x to y, which is a bad idea, but say I wanted to, GoRename will actually prevent that. So what happens here is x at the top, we're setting the value of 1 to x inside of our block. But the problem is, inside of there, we have a value called y. So if we tried to rename it, we'd actually just be updating y and never update x. And so we try to rename x to y using GoRename. So we're saying that rename the identifier x instead of do something to y. And we get this error. Renaming this value x to y causes a shadowing conflict. So it actually prevents us from these kind of dumb mistakes. Another one is an ambiguity conflict. And I went a little crazy on my naming. It's kind of Dr. Seussish. Dr. Seuss. I don't know how to say that. Dr. Seuss. Widgets, widgets, and flugets. So if we have our widget and our widget has a widget in it with a fluget, this is hard. Then if we wanted to rename widget to fluget, like this, that would be a problem because we already have something else named that in our widget. So we try to do this, and we get this renaming conflict. We'd basically be renaming something so we have a struct that has the same name. So while you'd get a compile time error in this, actually, in this case, it's actually embedded. So you may not even get, if you had 2 embedded fields, you may not even get that compile time error, but it just tries to prevent you from making those mistakes that are just so hard to figure out later on. So the SSA package and understanding your data and how it flows is really important, and there's so few tools out there to really understand what our code's doing underneath and to help ensure that we have correct code and safe code, that I really hope people go into not just even the SSA package, but the whole XTools package. There's the type checking, there's pointer analysis, there's call graphs, there's all kinds of amazing tooling in there, these primitives that we can use. We just need to build something on top of it. And this is just the beginning. I really encourage everyone to go at least look at it and just build something real simple. Just try to figure out some small use case for yourself to help improve your workflow and to do something with it. So with that, that's all. If you have any questions, I'd be happy to answer them.